So we're going to take a look at this stuff today. So, get the microphone a little better. Solving these equations, the first few are going to be a little more basic like last night. You're going to be able to see stuff like this where I've got two different logs. So we can combine them into one. This is addition of two logs, so we can combine them together with multiplication. So showing all the in-between steps, this would become log of the quantity x minus 7 times 3. We can distribute that 3 to both parts in here. So this becomes the log of 3x minus 21 will equal 2. Now that we're in logarithmic form, we can convert it to exponential. My base here is 10, so we can write this as 3x minus 21 equals 10 squared, okay, which is 100. And then we can write this as just our linear equation. So 3x is going to equal 121. And then we'll divide by 3, so x is going to equal 121 thirds. Okay? So there's kind of that similar basic stuff that we've seen last night. Yes, Casey? The 2 becomes my exponent off of my base, which was 10. Good question. Okay? So we'll have questions kind of like that. Thank you. Do you guys want to see another example of that, or is that similar enough to last night that we're okay? We're similar enough? Okay. Okay, and then the next thing we're going to take a look at starts to get a little more complicated. We'll show both of these because these ones are kind of weird. Okay. So something like 38. Here, you want to isolate. Let's try to isolate this variable. Okay, so since this is connected to the exponent, we can add 3 to both sides. So 9 to the 3x is going to equal our 78,465 now. We'll add 3 to both sides. How do we get an exponent or a variable out of the exponent? Put it in front, but how am I allowed to put it in front? What do I need first? We need the log. So we're going to take a log of both sides. Showing this in-between step, that means that we're taking a log of both sides. Log. And so now, because we have a log, we're allowed to use that property that will move that exponent up front. So we end up with that 3x log 9 equals this log of 78,465. And now we just need to get x by itself, so we can divide by 3 log 9. And so we'll end up with x equals log of 78,465 divided by 3 log 9. Okay, and there's our exact value. Again, type that into the calculator, you'll get your decimal approximation, take it out to 4 decimal places, and we'll be able to come up with whatever number that is. Okay with that one? That one's still kind of familiar. The next one's going to be the kind of weird, tough, confusing one. Okay? This one will be a little bit newer looking. So if I have exponents on both sides and I have variables in those exponents, what do you think we should do first? How can I get exponents up front? We'll take logs of both sides. Good. So when I take the log of both sides, so we'll work on this one here, I can move that out front, so this becomes x log 7. Okay, I skipped that in-between step, right? So that was log of 7 to the x. Variable can move up front. Equals the quantity 2x minus 1 times our log 4. Okay, similar idea. We took the log of both sides. I'm able to move this exponent out in front of the log here. And now you have a quantity times a log. You need to distribute the 2x and the -1 so that you can get the variable kind of isolated over there. So we've got an x log 7 equals 2x times log 4 minus 1 times, so this is just minus log 4. Now let's try to get our variables on the same side. I'm going to deal with positives to the best of my ability, so I'm going to actually add over the log 4 and subtract over the x log 7. Okay, I'll show that real quick. So we're going to add the log 4 to both sides. I'm doing that because I want to not have this negative log over here on that side. And then we're going to subtract the x log 7, because I want my x's all on the same side. Okay, so what we end up with when we do that is we'll have log 4 equals my 2x log 4 minus this x log 7. Okay, so I've distributed through, I've gotten my x's onto the same side of the equation, and now I'm going to try to get the x by itself. Okay, here you're going to notice you actually have a common term. You have an x in this one, you have an x in this one. Okay, just like we've done in the past, you can factor that out. So we have this log 4 equals x times 2 log 4 minus log 7. So all we did was we factored out that x from both of these logs. So there's two terms. The common term is x. We'll factor the common term out. Now you have two logs, okay, that you can combine together if you want, make this thing a little simpler. And I could move that 2 back into the exponent spot. So this could look like x times log 16 divided by 7, because that subtraction step. Okay, so that's just going to turn into a nicer left side, or right side there. And then to get x by itself, we're just going to divide because that's just a number there. So x is going to equal log 4 divided by log of 16 over 7. Yeah, it looks super ugly. It takes a couple complicated steps, but it's still all the same rules, same processes, same procedures to get there. Yeah, Sean. Why is it 16? Because I took this 2 and moved it in there, so it's log of 4 squared. So I could have also left it as 2 log 4 over 7. So there's a bunch of different ways that the exact answer could look, but at the end of it, they should all come to the same decimal approximation. Like we would have gotten something that looked slightly different. Like it could have been log 7 over 16 over negative log 4. I think is another way you could have seen it if we had moved things around a little differently up top. So that's what's going to be a little bit weird when you go to check your answers, is the back of the book may have it in a different way than you wrote it, but just check that decimal approximation, see if you actually do have the same answer, even though the exact answer may look different. Okay? And then the last piece we're going to look at tonight is going to be largely calculator driven. We're going to do some stuff that we don't have mathematical tricks to actually solve yet. And so we're going to let the calculator and use all of its algorithms and wisdom to do that for us. So if we go back and think about some of the things we've done in the past, where we have a couple of weird looking things. Let's say we have like the square root of something, and then I don't know, let's call it the logarithm, or let's say there's an exponential curve. Okay, let's say we have two weird looking curves that we know how to graph each of them individually, but if we were to combine them together, it's going to turn into this really kind of weird, complicated thing. We have no idea what it looks like. We can plug these into the calculator as these two separate equations. Okay, so for example, 41, we kind of know what 41 looks like. We know that if I wrote this as my y1, I could say this equals the cube root of x. And so I know that that looks something like this. And then we could write this as your y2 in the calculator. So you've got the natural log of x plus 5. So that's going to shift everything over here 5 units. And it's going to do something like that or whatever, right? So kind of generically what these look like. Okay. I don't know algebraically how to solve this, right? Something that's going to undo a natural log is going to throw this cube root into the exponent, and now I'm kind of stuck in this loop. But if you type these two into the calculator, and then what are we going to go find that'll give me the solution? The intersection point. So I can go find that little intersection point wherever it actually ends up being on the graph, and that will be my solution. Okay? So similar idea here, if I had two weird ugly things, you just go and look for the intersections. So if you use the zeros method or the intersections, the intersection of the graph, that's what we're looking at right now. The zeros method was the idea that we could take these two equations and turn them into just one. And so we could write this as the equation natural log of x plus 5 minus the cube root of x. And now when we do that here, that creates a 0 equals, right? So this is going to be our 0 for our y value. Now you go on to the graph, and so this thing turns into, I honestly don't even know what that kind of looks like. It's going to be some sort of a graph, right? And it's going to probably cut through at some point through the intercept. Now, instead of looking for the intersection of the two graphs, you look for the 0. That's the zeros method. So you'd go find your x-intercept essentially. So that becomes your solution to those two. Okay? So we'll do this one really quick on the calculator just to kind of see what it actually looks like. So you would go to your y equals, we'll type in these two equations. So x to the 1/3 is the same as the cube root. Okay, so again, fractional exponents, make sure we're kind of familiar with those. And then the other one was the natural log of x plus 5. Okay, so we've got these two things in there. I'm going to go turn my stat plot off right now so that doesn't show up. And so when we go to graph these, kind of as expected, we had that little bit of an S-curve, and then we end up with this exponential type look. So I can go find the intersection. My guess right now is, yep, right around there, which actually is pretty good considering what we're looking at. We were guessing there. Okay, so we can go to our second trace, which is calculate. Go find your intersection point, number 5. It'll ask you to find the first curve, the second curve, and then a guess, so we can scroll somewhere kind of over there. And we could guess there. Whoop. Just kidding. I went way too far. My calculator freaked out. Okay, let's go back to this. Second trace, intersect. Somewhere around there. Let's see if that works. Perfect. There we go. Second curve. And our guess. Cool. All right. So there's my intersection. So the solution to this system is that x equals negative 4.815. So that's what we should expect for our x solution. Now, if we wanted to go find it using the zeros method, what essentially what we want to do is we're going to combine these two into one equation. So I'm going to turn these two off real quick. And we're going to combine it into one equation. So we're going to call this You can also do this using your y bars if you're more familiar with that. Otherwise, you can just retype it. So natural log of x plus 5 minus our x to the 1/3. Now it's all as one equation. When we go to graph this thing, cool, kind of like we expected, it's going to be this weird looking curve here, but it's got an intersection point right around where we expected it to be. And so now to find that x value, go to second trace, which is your calculate, but we want to find the 0 of the function. So when you find the 0 of the function, we're going to go left bound. So we just scroll to the left. And then we need to go to a right bound of it. And then I guess somewhere in between there. And sure enough, there we go. It gives us the exact same x solution. X will equal that negative 4.815. Okay, so we don't have the math and the crazy complicated stuff to actually solve for these. But if we just think back to the general concept of, oh yeah, I can write it as one equation equals one equation. Let's graph the two and find the intersection point, or get it all into one equation so it's 0 equals stuff, and then figure out when is y equal to 0, your x-intercept, so to speak, and go find for that solution. So that's what we're going to work on today. You got a couple of weird, complicated looking things as well as the graphing.